Actually doing is guidance and control for autonomous space missions, and of course on the surface of both manuals. And so the big question is autonomy in space. Where are we and where are we going? Well, autonomy in space already exists, and it started all the way back in with Apollo 11, where everybody thinks Neil Armstrong was like the gung-ho piloting it down like a cowboy. But actually, they already had guidance controllers on board the spaceship that gave him a pretty decent estimate on where he was actually going to end up. And this run in real time, and is also done later years with some of the experimental missions that have been launched into deep space, for example, Deep Space One and Hayabusa missions, and also now OSIRIS-REx. All of these have different versions of onboard autonomous guidance, but primarily, they have been using open loop control or closed loop control plus some assistance. So basically retrospective controls, looking at what has happened before and then you compensate for it. So where is the future? Well, the future, of course, is to go forwards. So we are going to do predictive closed loop control, which is basically you look in what's happening in the future, not only in the past. There are many different ways to do it. The most easy way to do it would, of course, be, or straightforward, would be just to combine a guidance controller with a controller. So, for example, you solve a convex program optimization problem on board, and then you apply a controller to follow this in real time. This is complicated. Of course, you have the standard reinforcement learning, but what I'm focusing on is the model predictive control, which is basically, it does everything, which if you remember the talk we had a while ago, he also said, why not use model predictive control? That's also my motto. It fixes everything. So, what is modification control, and can we do it in real time? Well, first of all, we have to understand how it works, and for that, we of course need graphs. So, let's consider our spacecraft. It is acting in an environment given by some nonlinear function f of x. We don't want to use f of x. That is a nonlinear one. It's complicated. We have had enough complicated equations from electronic propulsions already. So let's just do a linear model, and then we predict into the future different paths where we can go given our linear model. Then we optimize, we find the optimal trajectory with respect to this linear model and our constraints, or our cost function and also constraints. And then we take the solution, apply it, and propagate, and then see where we are now. And then we repeat this process step by step at each discrete time instance. But of course, as you can see, there is isn't there a laser here? There is a small deviation here. We didn't exactly go where we thought we were going to be, and we're not where we thought we were going to be. So this error is a big problem. So this is because, of course, we used a linear model in a nonlinear environment. But we also have uncertainties from our solvers. We also have uncertainties from our measurements, because, of course, no measurements is exact. So this is what basically the gist of my research is. What if we don't want to do this autonomously? We want to have a guaranteed performance. So to deal with all of these uncertainties, let's just consider a tube instead. And we want to capture all of these models that we're propagating into the future into a tube, and we want to rather guide the tube where we want to go. So let's zoom in a little bit and see how this actually works. If you remember, we have a linear prediction model, which is given by this purple line, and we can have the actual nonlinear environment. And we can rewrite this a little bit, expand it out, and then collapse all the nonlinearities into this uncertainty term. And then we will have, again, a linear model with some uncertainty or noise. And this gives us the error. That is, we can describe the error now at the next propagated time step, given this equation here. So with this error equation dynamics, we can now modify our control loop. Instead of using the normal MPC, just applying the optimal input or optimal control where you have a whole input sequence, we now take advantage that we know the error and we are resolving this at every time step. So we have two terms here, the optimal control, which is the purple one, and the modification is the orange one. We take this, input it into our aerodynamics, rearrange it a little bit, and we get a system, an aerodynamics, which is actually stable. And then, of course, we know that if this is stable, at the next time step, we are going to close in onto our origin. And now the big advantage is, of course, we are resolving this at every discrete time step. So at every time step into the future, we are always going to converge on our future ellipsoid, as you can see here. And that ellipsoid we can call a robust positive invariant set. which is basically because we have uncertainties that are pushing us away, we are ending up being in some area around it. And we can compute that one. That is a nice thing. So summarizing, what I'm actually doing, we have a system, we use constraints, we are using actual real measurements, we have a certainty of our future position or tubes, we are modeling the environment, we are predicting the future, and we are controlling our vessel, which gives us the method I'm using, constraint output tube model predict control, which looks like this. And this is the one we're solving in real time on board. And it is, as you can see, it's linear and it's convex, so it's super easy to solve with good solvers. But can we do circumnavigation with this? Some of you might understand that a circumnavigation scenario is unconvex because you have a central keep out zone. So let's bring back our graphs. We have our spacecraft again. We want to go around the asteroid. We have the keep out zone. Instead of giving complicated equations of the asteroid, we just do an ellipsoidal keep out zone. But the important thing we do now, our solution from the MPC gives us a predicted future trajectory. And for now, let us just assume that we already have this trajectory from a previous solution. And we can then use this solution and we can linearize along it and find these intersection points here at the ellipsoid. And the nice thing about this is that then we can get this linearization and we will get these constraints. And now, maybe you can see that for a point that is, when we are optimizing now, we have a localized convex scenario. Each point will have, instead of this ellipsoid point, we will have one that is something like a triangle here, and we'll show you that it is basically convex. And local convexity in this scenario is also global convexity. So, we have our linearized and convex problem. So, does this actually work? Is it all a lot of nonsense with not any results? Well, we have actually tried it, and it works. And this is a circumnavigation scenario. This is sped up 10 times. The MPC is solving this on an equivalent of each Raspberry Pi, and is solving it in roughly 1/10 of a second. And each solution is solved every 4 seconds. So you can see here, we compare it with normal MPC. Normal MPC is just going straight into the hard keep out zone here. The black areas are where we don't want to crash. And our actual MPC output tube goes around nice and smooth. Can also mention that here we have biased measurements and also wrong measurements, and we have uncertainty in our thrusters. So there are quite a lot of uncertainties. But despite all this, we're actually having a more or less similar performance time in the end results. Other places where we apply this is also using a camera for navigation estimation. So in this system, the only measurement we have of our position is from one single camera, and they use a neural network to get the state. We put it into a Kalman filter to get some velocity estimates, and then we throw in the MPC, and you can see we go around the asteroids here as well. And finally, you can see here as well, and one interesting thing here, just notice that this is the aerodynamics. And you can see it doesn't converge to zero, because we can actually take advantage of the aerodynamics because we know we're always going to be inside it. So we can, instead of going towards zero, we can keep to the edges and actually use parts of the aerodynamics to our advantage. And here's some of my publications. I've cheated a little bit, just written everything in one, so it looks like I have a lot of journal articles, but it's only the last one here. It's submitted to Guidance and Control, Vesta Conference. We had one research day, which you saw the video of, and in 1 week, I'm going to the Netherlands, and we're going to take these things and apply it to the Hera mission, see if it's a feasibility study, and see what that happens. So, thank you for listening.